Good afternoon to all the participants. Vinila madam.
Sir.
Hello.
Sir.
Madam.
Okay,
available. Sir kuda join ayyaru madam.
Okay sir. Start cheyamantara.
Nenu maatladtanu. Good afternoon to all the participants. Today's resource person for our 1 week faculty development program is Professor B.K.N.Srinivasa Rao from NIT Warangal. Sir is available now, and Madam Vinila Garu is going to give some brief introduction about our resource person. Madam, please.
Very good afternoon to one and all. Let me take the pleasure of inviting or introducing Dr. B.K.N.Srinivasa Rao Garu as our today's expert. Dr. B.K.N.Srinivasa Rao is working as assistant professor in the Department of ECE, NIT Warangal. He is having 20 years of teaching experience. Dr. Rao completed his B.Tech in the year 2002 from Nagarjuna University. He did his M.Tech in the year 2008 from IIT Kharagpur. He pursued his PhD from IIT Kharagpur in the year 2017. His research interests are VLSI architectures for image and video processing, embedded system design, IoT, system on chip design, and network on chip. Sir published 3 patents and is an author of book titled Motion Estimation for Video Coding, Efficient Algorithms and Architectures. Dr. Rao published 10 papers in reputed journals and 12 papers in conferences. He organized 3 conferences. Presently, 3 students are pursuing their PhD under his guidance. He got 2 funding projects from SERB Government of India and NIT Warangal of worth around 27 lakhs. So we are very fortunate to have you as our resource person for today. Please continue with the session. Sir, please.
Thank you, madam. Sir.
Sir.
Sir, please make a presenter for.
Okay, sir.
Can I stop sharing?
Sir, I think sir is disconnected, I think, sir.
Okay.
Yes, sir.
Yes, sir. Yes, sir.
Sir is disconnected, sir.
Sir, sir, you are sir. Second, please join, sir. We joining tarvata we started the introduction about yourself and suddenly you are disconnected. Okay. Okay. Sir.
Yeah, good afternoon.
Good afternoon. Good afternoon to all the participants. Today's our resource person is Professor Dr. B.K.N.Srinivasa Rao Garu from NIT Warangal. He completed his BTech in the year 2002 from Nagarjuna University, MTech in the year 2008 from IIT Kharagpur, and PhD from IIT Kharagpur in the year 2017. Currently, Sir is working as assistant professor in the Department of ECE, NIT Warangal. He is having 20 years of teaching experience. His research interests are VLSI architectures for image and video processing, embedded system design, IoT, system on chip design, network on chip. He has 3 patents and is the author of book titled Motion Estimation for Video Coding, Efficient Algorithms and Architectures. Sir published 10 papers in reputed journals and 12 papers in conferences. He organized 3 conferences. Presently, 3 students are pursuing their PhD under Sir's guidance. He got 2 funding projects from self-government of India and NIT Warangal of worth about around 27 lakhs. And we are very fortunate to have a resource person like Professor B.K.N.Srinivasa Rao into our FDP. We welcome you all, sir.
Yeah, thank you very much for my introduction, and I welcome all the participants for this session. Today, actually, I'm planning to give some fundamentals about the video coding, and then a necessity of introducing machine learning or deep learning techniques into this video coding. Okay. Yeah. Can I start, Ria, sir? Hello.
Yes, sir.
Is it audible?
Yes, sir. Yes,
Yeah.
sir. It is audible.
Yeah.
Yes, sir. It is visible.
Yeah. Okay. Yeah. Video coding through machine learning and deep learning. Here, I'm not going to the a complete video coding part. Here, I have taken an example of video coding, video intra prediction, and within the intra prediction, the coding unit splitting is also a very important task during the interpretation. So I'll consider only one particular block within the video coding. Okay. And before going to that particular block, I'll give you the some fundamental details about the video coding, and then I'll slowly move on to the actual topic that is coding unit splitting. So here, the fundamentals are considered for the video coding. The introduction to video compression and what are the compression standards we have, and so what is the present days the video coding standard, and then we'll move to the machine learning techniques. Okay. Yeah, before going to video coding, so what is the need for going to a compression, video compression? Okay. So previously, if you take 10 years before or 5-6 years before, then the resolutions of your videos or maybe images are concerned, it will be very less. So maximum you may have HD resolution. So that means around 1020 and 1080 and 820 or 780 like this. So that is the resolution, and then those frames we need to process it. But as of now, if you are considered, everybody is talking about the 2K resolution, 4K resolution, and 8K resolution. So what is this high resolution? And then if you want to compress or process this much large size image or a video, how much amount of computational power do we require? Is it possible to compress by normal general GPUs or general systems? Again, there will be a task here. Suppose if you're not compress, then definitely the bandwidth required for us is generally it's a large. So here our example is concerned. So video increase in applications. That means we need for almost every application. If you consider the majority of your internet traffic is due to by the videos. So majority of the people are looking towards the YouTube, and there is a lot of movies are coming, and there is a lot of video content is available. Even the people who are utilizing in a positive way, they are getting the benefit out of it. But the thing, most of the people are utilizing it for their entertainment purpose and all. So the majority of our traffic is due to by the videos. So we need to compress it. Otherwise, it's not possible to give that much huge amount of bandwidth by the service providers. So, and the resolutions, higher throughput resolutions, everything is, and one more thing is we require a low power. So because most of the data is accessing by your mobile things, so we need to reduce the power. So resolutions are increasing, and somewhat processing capacities are increasing, and at the same time, the traffic is also increased by a huge amount. Okay, so the compression is very much needed in this particular time. So the frame sizes are concerned. Now we have the low resolution, that is VCD, and then DVD, then 720 and 180. So 180 is generally we call it as a HD resolution, and then the 2K resolution, and the 2K itself. So we have a 2 flavors, and then a 4K resolution. Now the people are talking about only the 4K. That means you just consider a size 4K. It is around 3840 into 2160 pixels. So this many number of pixels for one single frame. And how many number of such frames are required within a second? We require minimum of 30 or 60. And now the people are talking about 120 also. So the frequency is 120 Hz. That means the frame refresh rate is 120, means 120 frames within 1 second. So that means you consider 120 such one. Hello, can I continue?
Yes, sir. Yes, sir.
Yeah. I'm getting some disturbance, not disturbance. Maybe they are saying something. I don't know. Okay. So 120 frames we have, and each frame is of size this one. And with this resolution, is it possible to process by a normal mobile, normal or laptops and all? Again, there is a doubt. And not only this is what we are talking about, only the black and white images. Suppose if color is concerned, so we have a RGB pixels, then into 3 also need to consider. So everything is high resolution now, and we need to process it within a limited time. That means for a real-time applications are concerned, within 1 second we need to process. So 120 is such huge frames. So now the people are talking about how we can able to compress, or how can able to do the process as much as possible with a very high speed. So several images, as you know that the video is the several image frames combined in a sequence into constitute a video signal. Okay, so already I told you that there is a example of 120 frames or maybe 60 frames are sequentially combined, and which will be used for 1 second. And the frame rate of video processing system is started to be a number of frames sent out or received per second. That is maybe 120, 30, 60. So as the day-to-day consumer applications like mobile videos or communication or TV broadcasting is concerned, generally they are using the 30 frames per second. However, the rate can be varied based on the application. Suppose if you consider the medical applications, there in the medical applications, generally we require a huge amount of or more number of frames per second, because we require high quality videos or images to understand the internal things or to extract the content inside the content, we require the hue size frames, and at the same time number of frames also more or number of frames per second is generally large in the applications. Whereas a video conferencing sort of things means by the time you need not to have that much number of frames, you may have 15 frames. That is enough for the video conferencing applications are concerned. So generally, the video is divided into this number of frames per second as the time as an axis, x-axis, and the size will be on the y-axis. So here, the sequence of frames are connected like this, are transferred like this. So need for compression. Already I told you that what is the general need for our compression is higher bit rates. Generally, if you are not compress the video, then you assume I wanted to transmit a HD resolution image without any compression, then we require, so each pixel has a 3 colors, 3 into suppose frame rate is 60 into suppose the resolution is suppose 1000 sorry 1020 1080 1020 into 780 something like this. So then this is suppose this many number of bytes need to be transmitted within second. So that may not that much use the bandwidth generally will not have for the internets are concerned. So definitely it should be a compressed at least by 100 times or maybe 150 times like this, so that we can accommodate within a given bandwidth of internet or maybe mobile bandwidth. So how to compress now? Compression is very much required to have or to transfer a real-time videos or images are concerned. So what type of compression we can do? The compression is generally depending on uh, the type of redundancies we have. So one may be the spatial redundancy and perceptual redundancy, statistical redundancy, and temporal redundancy. So most of the times, the people are looking about the spatial and temporal redundancies. The spatial redundancy is called as the compression by using this spatial redundancy is called as intra-prediction, and temporal redundancy. That means the redundancy between the adjacent frames are called as a interprediction. So what are the compression standards we have? We have many number of the compression standards. If you observe from the 1980s to till now, so the compression standards are basically starts with the H dot 261, 263, 4, and present the standard is H dot 265, which is also called as HEVC. And also some other the standards are MPEG 1, MPEG 2, and MPEG 4. So MPEG 3. So these are the some compression standards which are universally accepted standards. That means whoever who wanted to compress the video, definitely they have to use such standards, because at the receiver side, they should know how to decompress that particular compressed videos or images are concerned. That's why we have to follow a uniform the compression standards. As of now, at present, the world is using HEVC. High efficiency video coding is the present standard. Maybe within 1 year or 2 years, we may get one more video coding standard, which is called as a versatile video coding (VVC). That is near future. You can expect that particular standard. But as of now, the HEVC is the present standard, and the people still working on this particular HEVC standard to improve the further improvement in the performance of the present standard. Okay, so we also worked on that particular topic. How can we improve the present performance with the new technologies like our machine learning and deep learning techniques. So, so what is the basic block diagram behind this compression standards? Any compression standard, if you are concerned, it may be MPEG standards or maybe H.260, 1 or 262, 3, 4. Any compression standard is concerned, basically they are using a block diagram. They are called as it is called as the differential pulse code modulation model. This is the basic building block behind almost all the video coding standards. So this is differential pulse code modulation. How or why it is called as differential pulse code modulation? That means, so in the differential pulse code modulation model we are using in this codec. So there in the differential pulse code modulation, generally we will encode the difference between the adjacent samples. The same model we are using in the video coding standard. That is, we are encoding the difference between the adjacent frames. So there in the normal DPCM, it is a one-dimensional signal. That's why we are taking the samples as the difference between the adjacent samples, and we are encoding it. And in this video coding standard, we are using the difference between the adjacent frames. That's why it is also called as a differential pulse code modulation model. So this is the generic, the DPCM, that is differential pulse code modulation encoder. But here, any video coding encoder is also having a decoding capacity also. So here, you just assume like our frame, the current frame is coming from here, and assume like maybe previous already some frames are coded. So that particular frame is frames, coded frames are available in the frame buffer. So that means I have a group of frames. So this is frame 1, suppose F1, and the F2, the frame 2, so whatever maybe the resolution is concerned. So suppose I am processing the F2 now. So then F1 is already processed by your encoder, and this is F1 is available at this place. So the basic idea behind this, the generic encoder is, suppose the adjacent frames are observed. Basically, most of the content is similar. You take a small example of you are watching some news. So at the time, the newsreader is reading the news, and within 1 second, how many movements we can observe? So only mostly we have a movements at his lip movement or maybe head movement sort of things only. Whereas if you consider the background sort of things, mostly it will be common, right? So why should I send a complete frame-to-frame information? Is it possible to find a difference between the previous frame and the present frame? Suppose previous frame is already signed and it is available at the decoder. So if I send a only difference between the previous frame and this present frame, and these differences will be added at your decoder, and which will construct the present frame by using a previous frame, and the difference between the previous and present frame will be used to construct your present frame at your decoder. Means already, so F1 has been transmitted there. So by any means, you just assume that it is transmitted and this F1 is available. Now here, I'm calculating the difference between, so F1 and F2 means when you are processing the F2, I just calculate the difference between this F1 and F2. And then if both the frames are almost the same, then you'll get the difference or which is also called as the residual. So that the residual information is almost 0, or maybe very less amount of information will be there at the residual frame. So this one, the residual frame information, if you add to the already existing, means here R is equal F1 minus F2. Okay. So already I have, or maybe, sorry, F2 minus F1. Suppose already I have F1 at the decoder side and I'm sending this residual information. So by using F2, sorry, F1, it's not F2, F1. So by using this F1 and the residual information, so they are able to create or reconstruct this F2 information. That means, so here F2 is equal to R plus F1. The same procedure they are following. So that means the adjacent frames are here using to create a residual information. The residual information is generally having the very less value, so that while transmitting this particular less value of information, we don't require a huge amount of the bits, or we can reduce the bit rate by using that. That's the basic idea behind this generic DPCM model. So, but the thing is it this subtraction or the residual identification by done on the complete frame? No, actually here, if you use the complete frame for creating this residual information, then here the residual information again have some medium amount of information. So to reduce that, generally these particular frames are divided into number of blocks. So each block, so in the previous standards, that is H.264, they have used the 16 by 16 block to process it. So that means the first 16 by 60 block of the present frame and the nearby surrounding areas of the previous frame. Here you consider this is F2 and this is F1. So this is previous frame. So around nearby areas of your F1 is compared with this one. Means where this particular block is available in the previous frame. Maybe that may be available in the some other place, not exact in the same location or same coordinates of the present frame. It may be available nearby because there may be a small movement may be happening. So because of that, this block may available in the some other place. So we need to identify where this particular coincide block is available in the previous frame. So that is called as the motion estimation. The process is called as motion estimation. So we have a different algorithms for motion estimation. So this is happening in the temporal redundancy. Means when you want to identify the temporal. So this particular process we are going to use. So, but if you want to transmit the first frame, by the time we don't have the previous frames. For our assumption, we don't have the previous frame. Then how it is possible? Suppose if it is subtracted from the previous frame is 0, we don't have. Then a complete information will be there with us. So is it possible to transmit a complete frame without any compression? No. Here also, we can estimate or we can identify the redundancy within the frame. Suppose if you have a background information, so for a newsreader, backside, suppose some white color board is there. So that particular board, entire board may have a almost the same amount of pixels or same pixel information throughout that particular board, or maybe a background is concerned. So instead of sending all the pixel informations, we can send or we can identify the correlation among the adjacent pixels within the same frame. So that is called as intra-prediction. Intra-prediction. Identifying of this redundancy within the frame is called as intra-prediction. So identifying the redundancy among the adjacent frames, so generally called as interframe redundancy. Interframe redundancy. Now, I'm going to this complete block diagram. Uh, we have this particular block diagram is helpful for yeah, uh, how this particular block diagram is going to work. So this particular block diagram will be applicable for both interframe redundancy identification and intraframe redundancy identification. So as of now, we consider like, because I'm focusing mostly on intra-frame. That means assume like my frame is a first frame. I don't have any previous frames, but within the frame I may have some redundancies. Means like a background information and all. So so the first frame is coming, and then during this interframe, the frame is divided into again the same macro blocks. So generally, for the previous standard, it is 16 by 16 size of macro blocks. Total image is divided into this particular size, fixed size blocks. That is called as a macro block. So that is goes to your transform block. What is the function of this transform blocks? This transform, basically, we are using the discrete cosine transform, DCT, as a transform module in this video coding standards. So it identifies, means it converts the spatial information into a frequency domain. So that means how many frequencies we have within the frame. So that means what is this frequency? How can we identify this frequency information from the frame? Here, the adjacent pixels. Suppose if we have a complete entire 16 by 16 block of same pixel intensities, that means maybe a white block. Just the information is white. So that means the white pixel generally is having a intensity of 255. So all the pixels, whatever the 16 by 16 pixels, that means total 256 pixels, everything is on this same information. So then what is the variation from the pixel to pixel here? That is we call it as a frequency. Here, no frequency variation is there. Everything we can call it as there is no frequencies are involved, because all the frequency, all the pixels are having same intensity. That's why we call it as it is a DC. That means zero frequency signal. The block is having only zero frequency signal. Remaining all the frequencies are concerned. All are almost zero. But generally, we may not have a entire block with one pixel value. So you may have a small variations. Suppose the first pixel is 255 and second pixel is suppose 250. So it means a small brightness variation, 250. Then the difference between these two is very small. That means it is having a low frequency, small frequency content. So these variations, adjacent pixel variations generally will give you the frequency information. Suppose the first pixel is 255 and the next pixel is suppose 0. That means this is white and this is black. So that means a sudden change of the information is there. That means previously it is 0, sorry, it is logical 1. And as of now it is goes to 0. There is a sudden change. That will give you the very high frequency information. So based on the pixel intensities by using your DCT, we are going to convert a spatial domain into the frequency domain, where if all the pixels are not having much variations, then low frequency information will be there and high frequency information is almost 0 after the DCT is observed. So this particular information again sent to the quantization. So we have a again, if the block for the transform or a DCT block is 16 by 16, then we'll have the frequency contents also, or frequency under frequency domain. Again, we have the 16 by 16 frequencies. So lowest frequency or zero frequency is the first one. And we'll have last or highest frequency in the bottom right side, right corner. So this, the top left will have a 0 frequency and this will have a very high frequency information. So how many frequency contents we have means, again, it is 16 by 16 frequency contents. The first frequency is 0 frequency, that is available at the top left corner. Suppose this, if you have more DC contents or pixel variations are very less, then how many such pixels are there? Suppose you just assume like the value is, maybe this is 1000. The first, the 0 frequency content is 1000 and very high frequency content is suppose 0. So that means the entire 16 by 16 frequencies are concerned, which will be varies from 0 to 1000. Then how many number of bits do we require to encode this particular information? So minimum of 1000 means for representing the 1000, we may require at least 10 bits, right? 10 bits. But representing the 0, we may require only 1 bit. 0 is 1 bit is sufficient. But to represent 1000, we require 10 bits. So how can we reduce this information? Because always we are planning to reduce the amount of data transmission or transmitted. So how can we reduce this number of bits? Here they are using the quantization. Means here the quantization is a fixed values. Suppose I have a frequency, sorry, the quantization block. Suppose if it is a 16 by 16 block, then quantization is also 16 by 16 matrix. So in that, the first one may be having a larger value. Maybe it is indicated with 100. So whatever the content which we have received from the transform coding will be divided by the quantization parameter. Suppose in the first quantization parameter corresponding to the first value of frequency is 100. Then the 1000 is divided with the 100. Then this is equivalent to 10. So like that, each and every frequency content is divided with the quantization parameters mentioned in the matrix. Suppose second one is suppose 50. Then this value is divided with 50. Like that. So the corresponding transform or frequency contents are divided with the quantization parameters. So that means we are reducing the largest number to a minimum value. So 1000 is divided with 100, then we are having a value is 10. So then to represent this 10, how many bits do we require? 4 bits are sufficient. To power 4 maximum 16. So we have only 10. So that 4 bits are sufficient. Without quantization, how many bits we require? 10 bits required. So that means the quantization is reducing the number of bits required. But the thing is, suppose the number is 1050 divided by 100. So here we are losing some information, right? So how can you get back this one? That is called as generally quantization error or quantization loss. So some information we are losing because of this quantization. Okay. So anyhow, it is quantized, and to represent this particular frequency content, we require 4 bits, maximum of 4 bits. Remaining all the frequency contents are less than 1000, so that the 4 is sufficient to represent your maximum. Previously it is 10, now it is reduced to 4 by using a quantization. So what happens at the decoders? So the 4 bits are transmitted and received at the decoder side. Suppose assume like the 4 bits are received. So the 4 bits are representing is 1010, so which is equal to 10. At the decoder side, the same quantization matrix they are going to use, so that this is previously at the encoder side we are dividing that number, and the decoder side we are multiplying that particular number. Means so number, this 100 is multiplied with the 10 and this is 1000. So that means, so after the quantization, again we are doing the inverse quantization by multiplying this, and then we are getting the transform coding frequency contents. So these frequency contents again given to the input of inverse discrete cosine transform. So this inverse discrete cosine transform will give you the again spatial pixel frame of a block of size 16 by 16. So that is the process, and that is loaded in your the frame buffer. Which means as a first block of the frame, like that. So the second block, third block, like that, all the blocks are processed, and the reconstructed thing will be loaded in the finally after completion of the frame. This frame buffer is contains the entire frame. Blockwise, it is added. So that is the general working of your DPCM model. So already I've explained this transform block. The first step during the DPCM model is this one. So discrete cosine transform, and maybe people is feel like if you lose some information during quantization process, it won't give any difference at your reconstructed frame. Yes, definitely there will be a small variations will come, but the thing is, our human eye is not very sensitive for the high frequencies. It is only, it can recognize the low frequency values. That's why we may not identify that particular quantization errors or quantization loss. Yeah. So here I am showing the small example with the 8 by 8 here. So this is 8 pixels in x-axis and 8 pixels in y-axis, 8 by 8. Suppose the 8 by 8 sub-area is concerned, that means that is the input which we have given to the discrete cosine transform block. And so this is generally a spatial information or a pixel information. So this, if you observe the pixel over here, so first pixel is 34 and next pixel is 34 and next pixel is 34 and next 33, 34. So that means the variation between these particular first 4 or 5 pixels is very small. So these are comes under now, these are comes under low frequencies, are almost 34, 34, 34 means zero frequency. So this is 8 by 8 spatial domain block or a pixel block, and that is converted into the, after the DCT, that is converted into 8 by 8 frequency domain block. The frequency domain here, the topmost left side topmost the number indicates zero frequency terms, zero frequency quantity, and this is first frequency or frequency 1, frequency 2, frequency 3, like this, like that. This number represents the very high frequency, almost 8 by 8 means it is a 64th frequency content. This is 64th frequency content. This is zero frequency content, and this is 64th frequency content. So if you observe the numbers on this frequency domain or discrete cosine result, if you see that, so maximum numbers will be available during low frequency regions, and remaining high frequency contents are concerned, this is very smaller values. So then can we neglect these particular values? Yes. If you neglect it, there may be a small loss. Definitely you'll get a small loss. But the thing is, as the number is very small, and that too it is related to the high frequency information, and for high frequencies, our eyes are insensitive. Our eyes may not be recognized these particular variations. That means at the time of inverse cosine transformer, if you keep all these values as it is, and if remaining pixel values, suppose not this one, whichever is nearer to 0, suppose this is 0, 0, if I keep like 0, this is 0, 0, like this, and transmitted these things into inverse transformer, and inverse transform will will generate the spatial domain pixels. That means after inverse transform, again, you will get this pixel information. So you will have a pixel information. Maybe 34 becomes 33, and this is 33, that 33, and 33 may becomes 31 like this. So small variations will come, but the thing is that much variation in the brightness or maybe variation in the frequencies may not be observed by our eyes. That's why we are using, means we are sometimes the people are neglecting the high frequency. The contents only process the low frequency contents. Then the processed information is reduced so that we can do the processing with very high speed. So what is quantization here? So quantization means here if you observe the numbers, there is a 6.4, 2.5, 0.3. So that means how to represent this particular number? Small as small is observed. So there is a -2 and -5 is the -5.3 is the smallest number, 5.3, and largest number is 257.1. Then if you use this floating point, then the number of bits represent to each frequency content is very large. If you use the floating point, then we have to make it as a integer. Integer means suppose 5.3 is there. This is 5.3. So 5.3, make it as a 5. So we may have a variation from 0 to or maybe -5 to 257. So for this one, or maybe suppose 251. So total difference is 256. For 256, we can represent with 8-bit information. But if you have a decimal numbers after the decimal point, then it is very difficult to represent how many number of bits. Maybe we require 20 bits to represent each and every frequency information. So the quantization is needed to integerize the given frequency contents. Here, you just see the example here. This is my suppose DCT information. Means after the DCT is applied on a 8x8 frame or a block, and then the quantization table or quantization matrix is this one. So this indicates this matrix size and this block size is always same. So this is 8x8 and this is also 8x8. So then the first row and the coordinate is concerned 0, 0. The first frequency information or a 0th frequency information is 1243 is divided with this particular 0, 0, the quantization parameter. This is called as a quantization parameter QP. So this number is division with this number, and this number is division with this number, and this 5 is division with the 10 like this. So all the numbers are division by using your quantization matrix. So the output, quantized output, is again integerized. The integer value is this one. Now you see after the quantization, most of the block is containing zeros, except the low frequency content. This is low frequency content. 78 is the 0th frequency content. And if you apply the inverse DCT or IDCT on this one, not only on this one, after multiplying the numbers with this one, that means 16 into 78. So that is the first frequency information. That is again applied to the inverse DCT cosine, sorry, inverse discrete cosine transform. Then again, you'll get the pixel information, original pixel information with small variations. Next, entropy coding. So entropy coding is some complex blocks. Just here for our understanding, just I will give you the Erlang coding as an example. So here the scanning generally, if you want to transmit this particular information, and at the receiver side, we have already the same quantization matrix is available at the receiver side, and we are going to transmit only this the output of the quantization process. So the quantized the matrix or quantized table or a block we are going to transmit to the decoder side. So at the decoder, the same block is multiplied by the subsequent the quantization parameters, means corresponding quantization parameters. That is 78 is multiplied with 16 and 2 is multiplied with 11 and 1 is multiplied with 10. So that means here the 2 is multiplied with 11 means here 22 you will have, but originally it is 18. So like that 1 is multiplied with 10. So that is actually we'll have 5, but here we have 10. So all zeros, multiply the zeros means again all the information is becomes 0, except 0 only will have very minimal number of the quantities. How to transmit through a wire or maybe a transmission media? This particular information I need to transmit. So then the scanning is required. Mostly in the video coding there is a jet scan. So the scanning is done like this. It's a jet scan. So jet scan is used, suppose. Jet scan is first they transmit the 78, then transmit the 2 and transmit the 1 and then 0 like this. Okay. How many number of bits we require to represent this 78? Maybe 7 bits are sufficient. And use the same number of bits to represent this number and then 0 also. But here we have a large number of zeros. So then by the time on the run length coding, what they will do is first non-zero quantities or non-zero numbers are transmitted by a possible number of bits. And then how many number of zeros are there? That is a run of zeros. We generally call it as a run of zeros. Suppose I have out of this 64, 61 zeros are there. Then they will transmit like 61, 0. So that means 61 can be represented by using 7 bits and 0 is represented with again 7 bits, means 7 plus 7. So this is 14 bits and this one each 7 bits means 21. So 14 plus 21, that is 35 number of bits are sufficient to represent or to send this entire block. So here 61, 0 indicates, so run off 61 zeros after these 3 numbers. Like that, they are using some entropy coding techniques. Nowadays, the people are using CAVLC, CABAC, content adaptive binary arithmetic coding or content variable length coding. So anyone they are using, but the reason behind this thing is like our run length coding and all. So entropy coding already I've explained. Now the motion estimation and motion compensation. This is generally for the temporal purpose. The motion estimation and compensation is to identify the redundance between adjacent frames. Here you see the motion estimation is I have a 2 frames. Okay, I have the 2 frames. This particular block, this is assumed like a previous frame, and this is our current frame. So this block is moved to this particular place in the current frame. So we need to identify where this equivalent block is available within the previous frame. So then now we need to search, means this is assumed to be a search area. I need to search within that particular block. So that search area is generally, if your block size is 8 by 8, then search area may be is 16 by 16 minimum or maybe 32 by 32. So that means it may be 16 by 16 pixels and 16 pixels. So throughout your frame, this is my block and surrounding pixels 16 by 16 or the search area, means within that particular block, I need to search where this particular block is available within this particular area. But you may feel like how it is possible? How can I identify this block is available in this particular area? So that means if you are subtracting this particular block information with the initially I started subtracting like this. So this is the block 8 by 8 block, and which is subtracted from this 8 by 8 block. If I get the 0, the sum of absolute differences are equal to 0. That indicates the same block is available at this place, right? So then we are going to identify how many pixels distance from the original. So that means here, suppose this is the block is starts with 2,3 pixels. This is suppose 0,0. Here it is 2,3. And here it is starts with 0,0. So that means what is the pixel variation or movement, pixel movement in this block? So variation is it is 2 pixels x direction and 3 pixels y direction. It has been moved from the previous frame to the current frame. So that particular information we are going to transmit. So already assume like this is previous frame is available there. So that previous frame, by adding the motion vectors, means motion vector is suppose 2,3. X-axis 2 pixels moved and y-axis 3 pixels moved. Then this block within the previous frame, that particular block is added by adding this number of pixels to that one. The corresponding, this is 0,0 is the coordinate, right? So for that, if you add the motion vector, then we will get the place like this. In this particular location, this block is added in the current frame, so that we'll have the same block in the next frame. Like that, we need to identify. So in the motion estimation is indicates identifying this particular block within the previous frame, where it is there, where it is available. So that is based on sum of absolute differences. All the pixel means all the block pixels is subtracted corresponding, means here this is my block. I am searching at this location. So the first pixel of this one and first pixel of this one subtracted plus. So that means x1 minus y1 plus x2 minus y2, this location and this location. Like that, entire block will be subtracted. And if wherever is SAD is small, that indicates more suitable or more identical block is available in that location. So for that, we have some algorithms. Instead of going to entire searching of entire block, so we may verify in some particular locations. That is called as a block matching. Here you see, here this is the frames captured. Almost if you observe this, background is same, only a small movements in their lips. So here small variations are there in the small lips location. Other than that, everything is almost identical. So that means if you can transmit only this differential information, then we need not to have a higher bandwidth are required. We don't require a higher bandwidth. Yeah, this is just like what I have said in previous thing. Here, suppose this car, this is previous location and move to this one. So we are identifying this particular thing in the previous one where it is there. So here it is. So this block is placed in this location. So this block is taken because this entire frame is available at our decoder side. So this block is added at this place, so that almost the difference is nullified or difference is very small. So the algorithms which identify this motion is called as a motion estimation algorithms. It uses the blockwise operation it performs. That's why it is called as block matching. Block matching in the name indicates. So we are matching this particular block in this one. That means current frame block, we are matching with the previous frame. Yeah, this is a clear idea about how search is taking place. So we have different estimation algorithms, full search algorithm, 3-step search algorithm, and then 4-step diamond search and hexagonal. And there are many number of algorithms. Recently also, there are n number of algorithms available. So these I was explained all the things about how this search algorithms will work in my textbook, motion estimation textbook. Now coming to what we have, what I was explained till now is completely a fundamental thing. So it is about fundamentals of your video coding or video compression, and that too, that is fundamentals is applicable for even advanced model also. So the present video coding standard, the previous one is H.264 or MPEG-4. So the present video coding standard is HEVC, high efficiency video coding, or it is also called as H.265. This is the present the video codec. Means if you want to transmit the information in a global environment, it's not a private communication. If you want to send a video data in a global environment, then definitely we have to compress by using this particular standard, that is H.265. So that the same decoder is available in the decoder place, because it is a standards are mentioned. So that the decoder side, they are going to decode it. Otherwise, if you use your own encoding techniques, then at the receiver side, they don't know how to decode this particular information. That's why everybody has to, if in a global environment is concerned, everybody has to follow some standards for compression. The same thing followed at the decompression side or encoding and decoding side. So our new standard is H.265. So what are the advantages of this H.265? Why you are means what are the new technologies adopted in this particular HEVC when compared to the previous standard, that is H.264? So this new standard video compression has a better performance than the previous standards. Performance means what is this performance? What type of performance, or what are the performance metrics? Here, the performance metrics are basically one is bitrate and the bandwidth, and the compression time. These are the some standards. So we define the performance of the video coding standards. So the HEVC standard is designed to achieve multiple goals. Here, while designing this particular standards, HEVC standards, they are considered like multiple goals. When H.264 is designed, by that time, maximum frame size is HD resolution. Whereas when the HEVC standard is designing by the group of people, by the time the resolution size or the frame size is gone to 8K resolution, means the size is almost 8 times it is increased. Then definitely a normal processor may not be processed this much of huge information. For each frame, 8 times size is increased. Then like that, 30 frames, minimum of 30 frames need to be processed within 1 second. Is it possible? That means 30 into 8 amount of time complexity has increased. So we have to address that particular thing. How can we address this thing? So while designing this particular HEVC, they mentioned or they consider the goals like multiple goals. One is including improved coding efficiency. That means the compression ratio must be increased. Previously, suppose H.264 is concerned, by that time, the compression is 120, 130 like that. Compression ratio is. That means amount of number of times the data is reduced. But whereas when you go for HEVC, it is increased almost double of that. Suppose previous standard is having a compression ratio of 120, now it has a 240, 300 like that. Means the coding efficiency is increased. ease of transport system integration, means the blocks which I've used is the data transferred from one block to another block is again it's easy. And data loss resiliency, whatever the data is lost, we can susceptible to that one, as well as implementation ability using parallel processing. This is the one more important thing. Suppose if parallel architecture is not possible, definitely we may not give you the result, real-time solutions for this HVC for 8K resolution or 4K resolution, means where the frame size or the resolutions are high. Definitely we have to go for parallel processing. Otherwise, real-time processing may not be possible for high resolutions are concerned. So HEVC outperforms its predecessor like H.264 AVC because it can reduce the data consumption by almost 50%. By considering all these parameters, goals, they are designed, and the designed HEVC is giving a almost 50% more result than, means less bit rate than already existing H.264. So that we can store this particular information within a less memory. So when compared to H.264, that is predecessor, and the present HEVC technology, then here one side we are having a bit rate, other side we have a picture size is concerned. Suppose for at the same picture size, means picture size is same, right? Picture size is same. This is HEVC model and this is H.264 model. So the H.264 may requires a higher bandwidth or bit rate. Suppose the bit rate is here 1 Mbps. This is 1 Mbps. Here this may be 0.25 Mbps or so not 25, 0.5 Mbps. That means for the same picture size, that means both are processing the one single HD resolution image. Then after processing by the HEVC, it requires only 0.5 MB of data rate in that particular channel. Maximum bandwidth of the channel is this much is sufficient. That means 0.5 Mbps is sufficient. But for the same resolution, if it is processed by H.264, then the channel bandwidth minimum required is 1 Mbps. And at the same time, suppose for the same bitrate is concerned, then the picture size, we have a low picture size for the H.264 and high picture size. That means for the same amount of bandwidth, maybe both are 0.75 Mbps. Then for this 0.7 Mbps, the resolution size by the HEVC may be 2K resolution, and by the H.264 may be 1K resolution only. That means for this bitrate, your H.264 process only 1K resolution images, whereas the HEVC process 2K resolution for the same bitrate is concerned. In both the ways, suppose if you have a quality, if you want a quality, then we can have, and if you want to have bitrate, less bitrate, then you have the less bitrate. Almost for all the applications, HEVC is ready to survive. So how does this HEVC is going to work? Yes, sir. So just
Sir, tell me, sir. Sir, tell me, sir.
Just 5 minutes. I'll take a break.
Okay, sir. No problem, right, sir.
Not more than 5 minutes. Just 5
Okay,
minutes.
sir. Okay, thank you, sir.
Right.
Okay, sir.
Shiva, please say.
Hello. Sure. Sure. Okay. నేను ఇప్పుడు తప్పకుండా. Yeah, sir, shall we start?
Okay, sir. Okay, sir.
Yes. Yeah, this is the HEVC block diagram. When you observe the difference between the generic model and this one, almost it is seems like the same. Here, the partitioning, one new block which is added with the HEVC is a partitioning, and then the predict transform. Transform coding means the discrete cosine transform, and then entropy coding, and then it will be compressed bit stream that goes to your decoder side, and inverse process is taking place at the decoder side. So encoder is the major new blocks which is introduced in HEVC when compared to your previous H.264 is the partitioning and the prediction process. So these two are major complex blocks which provide you more performance for this HEVC. So again, the internal blocks are concerned for HEVC. Here we have intra-prediction. So intra-prediction block and motion estimation and motion compensation. Combinedly, these two blocks will give you the temporal redundancy. And this particular intra-prediction block it give or provides you the redundancy within the frame. So generally, the frames are grouped together. The frame, suppose frame 1, sorry, frame 0, frame 1, the frame 2, frame 3, like this. So we have a group of frames that is called as GOF or GO group of GOP, group of pictures. For a group of pictures is concerned, maximum it may have a size of 8. So that means 0th frame, first frame, 2 frame, and then maximum at last we have a 7th frame. So next, after the 7 again, 0th frame will start. So that means 0th frame is generally called as a I frame or intra frame or information frame. So based on this particular frame, all the remaining frames are going to be constructed by using this temporal redundancy. So this first I frame is processed by using our intra prediction. So that means first frame, we need to construct almost original sort of thing with the different blocks. So that is called as your intra prediction. So intra prediction is our topic now. How we are going to predict the redundancy among this first frame or information frame, intra-frame. So intra-prediction is the process to predict the pixels of picture frame. Picture frame is the same information, same frame itself. The intra-picture prediction uses neighborhood pixels for predicting the picture block. So that means if you observe the entire frame, take here we have some object or maybe person, and this is completely everything. This is completely maybe of background information. So that means it has same information. Suppose when I'm division into number of blocks for processing intra-frame or inter-frame, we are division into number of blocks. So suppose I am processing this particular block. Means I want the information or I want the redundancy of this particular block. The redundancy means with the adjacent ones. So that means this particular block is already coded and this particular block is already coded. This particular block is already coded means. So when you come to JScan, so when this particular block is processing, by the time all these particular blocks are processed. So have information about the already decoded or processed blocks. So by using these particular blocks, if I can predict the information within this particular block, that we call it as an intra prediction. Okay. So what will be this block size? Is it a constant or is a variable? How can I get a efficient data or efficient compression with this size? Yes, definitely. If the size is large, the compression is generally large. But the thing is, what happens? We can lose the maximum amount of information. Suppose the discrete cosine transform is concerned. If I'm using a block of 4x4, size of 4x4, then for this 4x4, I'm applying the DCT and then inverse quantization. And then for this 4x4 block, that means out of 16 pixels, I may utilize either first four or maybe 5 frequency informations, and remaining maybe it is omitted or neglected. Like that, if you take the total 16 by 16 block size, so 4x4 blocks, within a 16 by 16 block size, we may have 16 4x4 blocks, right? 16 4x4 blocks. So each 4x4 block, we are utilizing maybe 4 to 5 frequency terms. If the size is 4x4. Suppose if I use the block size as not 4x4, if I am using a block size of 16 by 16, then out of this 16 by 16, entire 16 by 16, I may utilize again now 4 or 5 first initial frequency terms and remaining will be omitted. So based on this, I am reconstructing the entire this 16 by 16 block. But previously I'm using the 4x4 block. So more information will be there with the 4x4. But the problem is more computational power is required. If the image size is large, very large, then how many number of such 4x4 blocks will be required, and each will be processed. So then the processing time may increase. So if you increase the block size, definitely we can able to reduce the processing time. But the thing is, we may have a major information is going to be lost. So in the HEVC, what they have used, instead of using a constant amount of block size or a fixed block size, they mentioned that based on the content in the frame, it may be varies. From where to where it may be varies. It will be varies from 64 by 64 block to 8 by 8 block. That means if entire 64 by 64 block not having any variations, then this 64 by 64 block is transformed and then it will be transmitted at a time. But inside this 64 by 64 block, we have some variations in the content. It means some background information, foreground information, some objects are there. So then by the time we cannot process at a time for this 64 by 64. This 64 by 64 again division into 32 by 32. And again within the each 32 by 32 again division into 16 by 16. Again it is division into say 8 by 8 based on the content within the block. If the content is same, then we need not to go for division. That is called as the CTU splitting. Here the names are mentioned like. So this is about the intra-prediction in the previous standard, that is H.264. So within this, I have an entire frame like this. Now I'm going to process or predict this block 4 by 4 block. So already this capital M, A, B, C, D, E, and I, so J, K, L, all these things are already processed. Means these pixel values are available with us. So then we need to predict. Means how much correlation of this A is there with the previous in vertical direction, in the diagonal direction, or in the horizontal direction, or in the some angle with some angle. So this is defined with the total of 9 modes. So what are this mode? Here this is called as, first one is 0th mode, is a vertical mode. Vertical mode means, so first this A value is assigned to this particular all these pixels AEIM. Like that, B is assigned to this particular pixels and C is assigned to this. That is called as vertical mode. But we don't know whether the original pixel informations are the same as that of this capital A or not. So then how can we identify that one? So then we need to identify what is the error between the original and the replaced one, or the mode, 0th mode. So that is called as your error. Original pixels I have with me, and I'm going to predict by using this vertical mode. So vertical mode, suppose this is 5. I'm assigned with 5, 5, 5, and 5. Original maybe suppose this is 5, and this is 6, and this is 100, and this may be again 5, suppose like this. Then what is the difference here? The total difference we are going to identify. If this total difference is, if I suppose if I use this horizontal direction mode, here this is 100 and this is 6 and this is 5 and this is 5, suppose capital I, capital J, capital K, and so this is, suppose if I append here in horizontal direction, then I'm getting the less error compared to this vertical direction. So based on this error information, we have to select which mode, or which mode is providing a less difference from the original, that we are going to identify. So like that, the previous standard, that is H.264, has mentioned total 9 number of modes, so which consisting of the 0th are vertical, horizontal, and DC. DC indicates the average values. How they are going to calculate this average value, or directional, some directional, diagonal down left, diagonal down right, like that. So we have a total 9 modes. So the 9 modes equations are here. So here you see, if you are using a vertical mode, then AEIM is equal to A. So that means all these AEIM are append with this value. Like that, BFJN is append with B like this. That is called as vertical mode. So vertical mode is using this equation, and horizontal mode is using this equation, like that. So all the modes are mentioned with some equations. So we have to try with each and every mode, and which mode is providing less difference or less error, that will be selected. And to the decoder, we will mention like use this mode 4 or mode 5. Particular mode value is mentioned, so that at the decoder side, use the same equations to get this particular pixel informations. Because there also in the decoder side, so there also decoder is already decoded these particular pixel values before this block, so that these values are available at the decoder. So by using this, if I mention like use the vertical mode or mode 0, use mode 0 for this particular block. So then in the decoder side, it uses this particular expressions, these expressions to get this AE, all this 4x4 block. Okay, so this is called as the prediction of the pixel information within the frame itself. Now, suppose we have performed some experimentations on this particular thing, and we observed. Suppose this is my original information, original image. You just see that. So here, this is my original image and predicted with 4x4 block size. Means prediction size, block size is 4x4. Then this is my error. Error value is 2973. Then I have gone through, the size is increased to 8x8 size. And then the predicted, this is the prediction. And then the error is SAE is 4544, means error increased. The residual information is also, the difference from the original to reconstructed is large. Like that, if I use the 16x16 is like this, error is still further increased. Error is increased like this. Here, this is 32x32 block, then this is the error side. Error is this one. So SAE total error is 9861. So that means as the block size increasing, we are getting the error is more. So we have to, based on this, we can feel like, why don't we have a 4x4 size so that the error is generally less. But the thing is, if I have a size of image size of 4K resolution, then how many such 4x4 blocks are required to predict it? Then how much time it takes within one frame itself? Like that, we need to process 30 frames per second. So then it is not possible. Then, so the HEC is mentioned. So intra prediction is mentioned like, so from the previous thing, H.264, one thing we can conclude that the division of these blocks or the size of this block is gives you the very important role. If you take the larger size, processing speed increase, but the thing is error increased. If you reduce the size, processing time increase, it reduces the error. But for larger frame sizes, taking a small block size is not viable solution. So HEVC mentioned that as a solution for that, they mentioned like, so all the video frames generally, suppose this is my 8K resolution video. From here video, so may have a 60 frames within a second. So each frame is considered out of the 60. Each frame is divided into coding tree units. CTU indicates coding tree units. The size of this CTU is basically they mentioned as 64x64. Each CTU size is 64x64. Then each CTU, one CTU again divided into 32x32 with a depth. 64x64 is called as a depth 0. And this is just like our tree, expansion of tree. So this may be divided into 4 CUs of size 32x32. And if this particular block doesn't have any variations in the pixel informations, or it may be related to a background, then we need not to divide this particular block further, because the total information is almost the same. Then if you go to the transform block, then we can have the frequency information, and the low frequency information is sufficient as it doesn't have a variations within the block, so that we need not to worry about the high frequency contents and all. But suppose you consider this particular 32x30 block, inside that there is a small objectives are there. There is a variations in the pixel informations. Then again, this particular thing again we are division. And Again, this 16 by 16 block, again, it may be divided into 8 by 8 block based on the complexity in the pixel informations or the variations in the pixel informations. If more and more, suppose checker board is there. Or maybe a lot of variations are there within the small size. Then we have to go for smaller blocks for transform or coding it. Just see here how it is going to divide in the HEVC. So 1024 into 768 is the frame size. So it is divided into, so 1024 and 768 is the frame size. It is divided into number of 64 by 64 blocks. Means this block color is indicates it's a 64 by 64 pixels block. Then this 64 by 64 block again division into 32 by 32, and then maybe again division into 16 by 16. And based on the internal pixel variations, again, it is also maybe division into 8 by 8. So this is called as a tree structure, and the root is start with the depth 0. This 64 by 64 block is divided into 4 32 by 32s, which is mentioned with the number. You see, this is 7, means number for this block is 7. Okay. How the numbering for these blocks are given? Initially it is divided into 4 32 by 32 blocks. Again, based on the information, again it is division, and this is also division. And just scanning order is there used for labeling it or numbering it. So here 7th block is not division or splitting further because it doesn't have a variations within block like that. So depth 3 up to the size 8 by 8 size they are accepting, means the standards mentioned are recommended up to 8 by 8 we can go. So these are the general basic terms which are you going to use for divisioning purpose. The coding tree unit, it is a 64 by 64. It is divided into coding blocks with the size 32 by 32 and 16 by 16 and 8 by 8 like that. So this is just scan order. Generally, while transmitting the data, this is the order which you are going to follow. And processing also, block-wise processing. First, we are going to process this particular 0th block, then second block, first block, second block, third block like this. Processing is also we are following the same order. Processing is prediction purpose again. How we are going to predict this 0th block. So for the 0th block, suppose we don't have a previous blocks which is already decoded. Then what we'll do is we'll increase the frame size, that is append. Appending is taking place. Based on that appendment, we are going to do the process. Yeah. So in the 264, we have used the 9 modes for prediction purpose in the intraframe. But here HEVC they mentioned total of 35 modes. So Jure is planar mode and one is DC mode. DC means average we are going to take. So the directions are also mentioned and equations are also given by the standard how to calculate this. So for example, here we take this is the current block and we need to process suppose this thing and this thing. So then you assume that already this is processed. This right PU is already processed. Then we can estimate this particular pixel information by using these particular modes. So then that is the prediction purpose. But before going to the prediction, we need to identify what is the block size. The block size is very much important. If you know the block size, then prediction may be done. But the how to get the optimal value of this block size. Suppose each block is divided into 8 by 8, then definitely will have a good result. But the thing is, the processing speed or the processing computational power required is increased like anything. So wherever is unnecessary, we need not to go for splitting, and wherever is it is compulsory to split because the internal variations are large, then we need to split. So optimal splitting of this CTU is a major thing in our intra prediction. Means how we can able to division these blocks. So in this intra coding, they mentioned the intra coding flow chart is mentioned like so start with CDU means how we are going to split this CTUs into CUs, means smaller size 64 by 64 is our CTU. That sometimes we need not to split it. If you have a background information and pixel variations are 0, then you need not to split. But the thing is, suppose we have a clumsy of pixels, everything is variation. So one is having a 120, next pixel is having a 200, and next pixel having 0, like that. If you have a lot of redundant, a lot of variations in the pixel information, so by that time, definitely we have to split it. So optimal splitting is done by using this particular flowchart. Means this is mentioned by the HEVC experts, HEVC standard fellows. So there they mention like the first start with CTU means I am taking the 64 by 64 block as my reference block or first block, and then the depth is for this one depth is initially it is depth is set to 0. Depth is 0. Execute HAD or this is called as a rough mode decision cast. This yellow color block, it identifies the HAD, Hadamard transform value. Here we have equations for calculation of this. Yeah. So some equations they have given how to calculate this Hadamard transform values. So by using that, we are going to calculate this Hadamard transform. Means each block or entire this 64 by 64 block first start with adjacent 64 by 64 block. This side we have a 64 by 64 block, and this side we have a 64 by 64. So by using these particular blocks, we are going to estimate or predict this current 64 by 64 block or CTU. But what are the modes mentioned for this prediction? So total of 35 modes they have mentioned, right? So these are the 35 modes. Each mode have equations to predict the pixel informations. By using that, so first CTU, all the 35 modes, the Hadamard cost is calculated, and out of which for the size of block size of 64 by 64 and 32 by 32, it uses which Hadamard or which mode is having lowest value of HAD, Hadamard transform value. That means the error value. Out of 35 modes, for the block sizes of 64 by 64 and 32 by 32, which is having which mode are the least three modes, which has are a modes, 3 modes which has a less value of HAD. Identify, and then it goes to the next step. This is the first step, identifying of Hadamard transform values for each mode of 35, out of which it selects 3 modes, least HAD modes, and then goes to the MPM. This is most probable modes. Most probable mode indicates, suppose if we have the block like this, for a previous blocks, it come from the top or maybe vertical mode. So vertical mode is this is vertical mode. It is constructed using vertical mode. Previous block for this block is this one, that is most probable mode is suppose 0, and this is also most probable mode is 0. Then definitely the probable mode for this one is 0, right? So like that, it identify what is the most probable modes and which will be added. Means already 3 modes we have identified here. Least HAD, 3 modes identified here, and then most probable modes, maybe here 2 modes we have identified here, which is added to this one, means total 5 modes are there. For all these 5 modes, here rate distortion cost is calculated. Again, we have some equations for calculating of this RD mode, RD cost. Then for all these 5, they calculate this RD cost, and then if the depth size is, because starts with 0, it starts with 0, depth size is less than 0 or not. Yes, it is less than 0, definitely. Then it goes to increase the depth. That means again it division into 32 by 32. Right. So again 32 by 32, same process it follows, and then again it goes to the 16 by 16. So finally, if the admod cost or probable mode for smaller block is, that is 8 by 8 and 64 by 64 are same, then the block will not be divisioned. The depth information will be provided is equal to 0. That means it is indicating that no need to division that particular block. Right. So it decides which depth we need to stop. Next one, rate distortion optimization. Here are some expressions they have given for calculating this rate distortion. But the thing is, every time if you want to calculate the depth, which depth we need to select, either 0 depth or means divisioning is required or not. If divisioning is required, at which level, where which depth we need to division. So we need to stop at depth 1 or depth 2 or depth 3. So these things generally will comes after completion of all this particular process. This is called as a iterative process. Iterative process means for depth 0 to 3 need to calculate, and all the modes we need to calculate. So it takes a lot of time, means most of the complexity involves in this particular block itself. That means the divisioning of the CTUs is extremely a complex thing. That's why we have selected that particular thing. Can't we do this particular thing with our machine learning? Yes. Why can't we do it by eliminating this iterative process? So with that, we started our the findings. So one of my PhD student is Hari, has started working on this particular thing. So the rate distortion optimization, which is mentioned by your HEVC people, is having involves a lot of the complexity. That's why we have entered into this machine learning models. So in the machine learning models, also we have used the different texture information. So we know that divisioning is required if it has a lot of complexity inside the block. That means the pixel information, that is called as a texture. Texture information is changes. Then only we need to, or texture, lot of texture information is there. Then only we need to split it. Otherwise, we need not to split. Then now overall, the block we have categorized into 3 categories. One is non-homogeneous, homogeneous, and then recursive based, means class A, class B, and class C sort of thing. So here, class A indicates non-homogeneous. Non-homogeneous means definitely it has a variations in your means we need to split it. Non-homogeneity means variations are large. Definitely we have to go for split. Okay, and then other thing is class B block, which doesn't have much variations within the block. So for that, we don't require the splitting. And the other block is having intermediate sort of thing. By looking into that, we cannot decide whether it can be split or not. So that we call it as this normal premise. For that, we are using the normal processor. So here in the proposed model, what we have done is, so first of all, we are identifying what are the non-homogeneous blocks and what are the homogeneous blocks. So the non-homogeneous blocks, so we are not going to send it for splitting, and homogeneous blocks, sorry, non-homogeneous blocks are sent it for splitting without any further calculations, and homogeneous blocks are stopped for splitting. We need not to split it. Means it is decided that homogeneous blocks are not going to split. Only problem is major problem with the blocks which are having a intermediate sort of things. So for that, we used the same procedure which is mentioned by the HEVC. That means RDO cost. It is a iterative process. Here, for a entire block, suppose we observe that for a frame, we division into number of CTUs. Each CTU, suppose this is my CTU. And here I observe that the entire block is not having any variations. That means it is homogeneous. Our category, it is mentioned as class B. And this has a lot of variations. Oh, big variations are there. Then for that, I have taken a class A. And here another block, which may have small variations like this, whether we need to split it or not. So that will be categorized as a class C. Class, how to separate it out, whether it is a homogeneous, non-homogeneous or intermediate category. So for that, we have used the support vector machine in the machine learning, SVM. So SVM is classifies whether it is belongs to class A or class B or class C. Class A, definitely we have to go for splitting without any further. And class C, it is difficult to tell that splitting is required or not. So by the time what we have done is we have used, if you see this block, this is my algorithm, proposed algorithm. Here, calculate by using SVM class B. If it is belongs to class B, then current depth is the final. We need not to split further. And class A, so splitting is required. So go to the next depth. Suppose if it is in depth 0, then goes to depth 1, and again split. Again verify within that block. So whether means 64 by 64, again splitting is required or not. If it is categorized as a class B, then splitting is not required. Class A, splitting is required. Class C, we don't know whether splitting is possible or not. By the time we are using the original method of splitting mentioned by the HVC. So like that, the entire frame is observed. Almost SVM can able to classify, support vector machine classifies almost 60% of the blocks, and only 40% or even less than 40% for some videos we have observed that 30%, 20% of the blocks only having a doubtfulness, that means which comes under class C, they only send it for iterative process, and remaining all will be without iterative process. So with just SVM we have classified. So because of this, almost 60% of the time has been reduced for splitting when compared to the methods mentioned by the HVC people. So what are the features, means how SVM is going to classify these sort of things? We have taken some features. So here the features are root mean square error and sub CU coding difference and standard deviation, and then directional complexity. These are the some parameters. We have equations for calculation of these parameters, and all these parameters has been given as an input for your SVM. And based on this particular parameter, this SVM is classifies class A, B, and C. Means it's a 3-class model we have defined for the SVM. Yeah, you see, the classification means after calculating these parameters like directional complexity, standard deviation, and RMSE, all the things as given as inputs. And not only all the inputs given, we have verified, is it possible to separate it out with one particular parameter or 2 parameters or 3 parameters like that. So we observe that 2 parameters are giving a better result compared to remaining all. And here, if you see, first we started with the 2-class model, and 2-class model, the blocks which are in this particular area is having the dilemma whether it will be belongs to class B or class A. So separating it out of this particular class blocks is difficult. That's why again we went for 3-class model or 3-class classification. Here in the 3-class, so class B is mostly it is class B means all are homogeneous. Information, pixel information is less, and here this is, so inside the texture complexity or pixel variations are more. So this definitely goes to splitting, and this not split, unsplit, and only the category of this category of blocks send it for rate distortion optimization, which is mentioned by your HVC. So, and we have done the some calculations instead of using only one, we have verified with the two feature here, only one feature. Edge magnitude is the one feature. This is given and identified that the quality is generally less, accuracy is less. And then we have used the directional complexity as well as SCCD. Sub-CU complexity here. This SCCD is sub-CU complexity, and directional complexity and RMSE, directional complexity versus standard deviation. So these are the particular features we have mentioned are given to the SVM, and by the time it is providing the accuracy of for a block of 64, accuracy is almost 93, and 32 by 32 it is 87, and 16 by 16 it is 85 like this. So, and later we observed with three features as given as input for SVM, and then observed that almost again the accuracy is not increased. Then we observed that, and we concluded that the two features are giving a better result compared to other things. If you go for three features, complexity increases, but we are not getting the benefit out of it. So that's why we stopped with the two features. These are the features we have considered as inputs for your SVM to separate it out, which class it belongs to. So these are the projected sort of things. And okay, we have developed this model, and then how can you verify with the standard model? Standard is mentioned with the RDO cost. So the splitting of each and every block must be done with the RDO cost. But here we have calculated or splitted by using some SVM and some with the RDO cost. Then how can you verify the performance, whether this one is giving better result or the standard is giving better result? So that's why we have gone through the standard model. Means the HM15 is the software which simulates the HVC standard. There we have modified the interpretation model with our proposed thing, and keep the remaining all the blocks are as the same as that of our standard, and then simulated the models. And we observe that the total time with the RDO cost, which is traditional HVC model, and compared the results with our model, then the total time for encoding is reduced almost by 65% for the class. Here, this class and that class are different. Here, this class A is videos which belongs to this class A, like that. That is traffic model, people on street, and kimono. These are the data some standard videos we have considered, and these videos run with the standard HEVC model and run with our proposed model. Then we observe that these are the variations. Means our model is given very less time. Means it is encoded within less time. So variation is almost 67% time has been reduced. And data set preparations and all, we have taken a lot of data sets. And after that, okay, with machine learning model, we got some benefit. Then why don't you go for deep learning models? Then we have also tested with the different deep learning models, existing models, and by modifying the architectures of existing models according to our requirement, that is CTU divisioning model, we have modified the complete architectures by using. So one model is we've mentioned, this is the CNN architecture, which is done by my MTech student. He is working in Qualcomm. He has performed this particular model, and observe that again it is compared with our standard HEVC, And this also, here also we are getting almost average we are getting 70% variation, means our model is 70% less time. It takes the less time and compared to standard model. And next, one of the other deep learning model which we have used, VGC16, but here we mentioned as CU VGC16. CU VGC16 means coding unit splitting. According to the coding unit splitting, we have modified the VGC16 model, and then we applied. And directly, we are not going to apply the input from the frame. Here, what we have done, we have done some pre-processing. So because of this pre-processing, the number of blocks which processed by, or the total amount of information which will be processed by our deep learning model has been reduced. So the input must be pre-processed before being applied to the two deep learning models, that is 16 and 19. Because of this pre-processing, the input data frames, the spatial resolution is greatly reduced and allowing the neural network model to adapt. So because of this, suppose my frame size is 2K resolution, maybe it goes to 1K resolution or reduces than that, because this sizes will be depends on our requirement or application to application, it will going to vary. And these are the models which we have used, which is the 16 and modified according to our CTU partitioning. This another model. And we have architecture details are concerned, how many filters, how many layers we have used and all. So input and the convolution 1 and convolution 2 layers. Convolution 2 layers are of the filters 2 filters and kernel size of 3 by 3. And activation function we have used ReLU. And based on requirements, slightly we have modified the VGC16 compared with the traditional VGC16. Yes. Finally, what is our output with this machine learning models or deep learning models? So for a given CTU, we are able to observe like the first block, we need not to separate it out or we need not to split. And then the depth level is mentioned as 1. And this is 1. And then again, the third block is concerned, again, it is split into 16 by 16. Again, it is split into 8 by 8. So like that, the total divisioning or splitting of the block is comes out, means output of our machine learning model is like this. Then how to code this one? This is my output, means depth level is 1 only. So how to code this one? How to code this one means here the actual total size is considered is like this. Suppose this is entire one and this is entire one, right? And then so this is entire one. So then this is taken as a 1 and this is 1, 1 and 1. This is also 1, 1, 1 like this. So all the 8 ones. And then this is 2 and this is 3. All this completely it is of 3, division is 3. And then this is 2 and this is 2. Here 4 ones, 1, 1, 1. And this is 2, 3, 2, 2. And this is 1. Sorry, 1, 1, 1 like this. So this particular 16-bit means for each 32 by 32 block is coded with 4 bits. So that 4 bits are mentioned here. First 32 by 32 block, second 32 by 32 block. So that means first 32 by 32 block of depth 1 only, and second 32 by 32 block of depth 1 only, and third 32 by 32 block is split into depth 2. That means this is depth 2, and then 3. This is goes to this particular block is goes to depth 3, and again remaining 2 are depth 2 again. So this is depth 1 only. So this particular depth information we are going to give as output, so that based on that, the prediction block size is mentioned, and the model is going to predict the pixel values by using a 30 5 modes mentioned by the HEVC. And we got the result when compared to original VCC 16 and VCC 19. Our modified architecture has given some better result compared to means the testing accuracy and testing loss is concerned. Less loss and high accuracy we received after modifying the VCC 16 and 19 models according to our CTU splitting model. And these are some other results. And these are the data sets which we have used. Yeah. So finally, coming to our conclusion, the coding unit splitting is a very complex block within the current HEVC standard. So that involves the standard specifies that rate distortion optimization is the measure to split our coding unit, coding tree unit. But it involves the iterative process and takes a lot of time. That's why we have observed the machine learning models may useful in this particular model, or in place of RDO, we can replace the machine learning models and deep learning models. And finally, we observe that these two models, machine learning and deep learning models, as given the encoding result or encoding time is reduced by almost 70 to 80% compared to the standard HEVC methods. So, so that means this is a one feasible solution for coding unit splitting. Maybe the next standard, that is versatile video coding, may adopt these machine learning models in place of RDO. Right. Yeah. So thank you very much for giving this opportunity. If you have any questions, you can ask me.
Thank you, sir. If any questions from the participants? Any questions from the participants? You may please post the message in chat box.
So thank you very much, Riaz, for giving me this opportunity.
Thank you, sir. So the participant doesn't have any questions. Very nice and wonderful session from your side, sir.
Yeah.
Very much, sir.
You can consult me through my mail ID also, srinu.bkn@nitw.ac.in.
Oh, okay, sir. I have, sir.
Yeah.
Any questions from the participant side? I think there are no questions from the participants, sir.
Okay.
Okay.
Thank you
Very much, sir, for accepting our invitation and for the presentation.
So I wish all the best for all the participants. Congratulations for the organizers.
Thank you very much, sir. Parthu, sir.
Thank you, sir. Thank you very much.
Parthu, sir. Sir, yeah, Parthu sir is available with us, sir.
Yeah. Parthu, how are you?